Hi everyone, and welcome back. This is going to be our next part in the electronic introductory thing, first steps, electronics-y stuff. So we're going to be doing resistance today. We're going to kick off with that. We're going to try and aim towards looking at resistors at the end. May get there, may not. So we'll play it by ear. So yeah, and get you introduced to Ohms Law and might make a start on that as well. See how things go. Anyway, let's make a start. So then, resistance. Yeah, the next big step. We've done voltage and current, now resistance, and hopefully we'll tie things together. So what is resistance? Well, we'll have to take a step backwards into one of the previous ones, because resistance is related to conductance. Now I've explained conductors have conductance, and it's a measure of how well they conduct current. The higher the conductance, the more conductive the material, the more current flows within the circuit. So taking that basic circuit, we just had the voltage and connected the positive to the negative, you had a current flow. So yeah, if that's a really good conductor, that connection, maximum current flow. If it's a very bad conductor, then less current flows. Or if it doesn't have if it's got zero conductance, it's got no conductance, then no current flows whatsoever. And we take it to be an insulator. Well, resistance is very similar to that. So much so it could be brother and sister. They're twins in effect, because they're one and the same thing, just from different sides, from a different perspective, you could think. And in electronic engineering, we use resistance more. We generally use the term resistance rather than conductance, unless we're talking about materials and things like that. But generally in circuitry, it's resistance, and resistance is the opposite of conductance. So where we had a very high conductivity, very high conductance, you've got a very low resistance. Okay, resistance is all the way down there. Resistivity is nothing. Maximum current flows. So no resistance in the circuit, maximum current flows. On the other hand, conductance, if it's very low, no current flows. Well, if it's in terms of resistance, it's very high. You have a very, very high resistance. Hence, something is very resistive, okay, got a high resistance to it. Bugger all current flows, okay, and yeah, so things with extremely high resistances, almost unmeasurable resistances, are our insulators. They don't conduct current, they resist the flow of current. And to put that into context, an analogy if you were, let's have a think. Yeah, swimming baths analogy. Okay, you go to a swimming pool, Water World or wherever it is that you're going to go to, get changed into your budgie smugglers, and you go running off to the pool. Now you can get from the changing room or your locker or wherever to the pool very easily. Okay, nothing's resisting you, nothing's impeding you. You can get from A to B really, really, really easily. Now, you jump into the pool and you think to yourself, ah, crap, I don't want to be over here, it's too packed, too crowded, I want to be over there. So, now you're in the water, you want to get to the other side. Well, moving in water is not as easy, is it? We've all done it. Got into the pool, want to get over to the other side, it's too crowded, so you got to walk there, you try and do it fast, and the water's resisting you. You can't get to the opposite side of the pool particularly easily. Well, reasonably easy, but it's a lot harder than getting to the pool. Okay, because you've got this water in the way, it's impeding your movement. You have a substance there that's stopping you from moving. That's basically what resistance is. And in terms of electrical circuits, it's the current. Okay, you would be the current. So resistance, affects current. And going on from there, yeah, let's apply that to our circuit. Now, our circuit that we've been working on has been a voltage source that's been connected with a wire. As I said, all materials have resistance, and wire has a resistance associated to it. So yeah, let's work out resistance of our piece of wire. And yeah, then we can start plugging in numbers, and we can do a bit of Ohm's Law. And I'll explain Ohm's Law after this, because we'll have some numbers to work with to our circuit. So let's go down onto the screen, and we'll, I'll show you how to do the resistance of a wire, a little bit of resistivity, and yeah, then we'll start plugging in some numbers. So then, resistivity of a wire for our circuit. Right, well, let's do our circuit first, what we did before. So we've got our voltage source, and we'll call that 1 volt. That's our voltage source. Let's say positive, negative, arrow, direction of the potential. 1 volt, and connecting our positive and negative together so we can get current is a piece of wire. So here we go, that's our piece of wire joining the making the circuit, and we have a current flowing down this wire. So current is expressed as I, it's measured in amps. Our wire is going to have a resistance. Now resistance has the uses the symbol R, and it has the units. The units of resistance are in ohms. So R is in ohms. Symbol is the omega symbol. So resistance is measured in ohms. Well, let's just write that down. OH. It's the ohm, okay? Just so that you got an idea of that. Let's get rid of that now, because we know all about that now. So, what we need to know is, what is our resistance of our piece of wire? Because if we know that, then we can work out the current based on a 1 volt at the input. That's basically Ohm's Law. But we need to know our resistance first, so I'm just going to take you through, just to explain to you how to do the resistance of your wire. Now then, the equation for working out the resistance of the wire, so resistance R is equal to rho. Rho is the resistivity of your material. That's basically a constant value that's given to all the elements. Okay, you've got your periodic table, everything in there that's conductive that we know about. It's all given a particular resistivity. It's a constant value for that particular element, and resistivity, or rho, is measured in ohms per meter. So our resistance of the wire is rho, which is ohms per meter. Bloody hell. Multiplied by the length, isn't it? So, right, I mean, multiplied by the length of our wire, divided by the cross-sectional area. So if let's say, this is our wire, so we've got a squiggly wire. There we go, that's our wire. L would be the length. Cross-sectional area would be the area of the face of the wire. Okay, it's the end of the wire, so in this case it will be the circle, and the area of a circle is what is it? It's area of a circle is equal to pi r squared. So it's the radius squared multiplied by pi gives us the area. That's our area, length, length, and so on. Now, depending on what material that we use, we can plug in our constant value for our resistivity. We can measure our length, so we know our length, and we can calculate out our area by measuring the width of the cable. If we got the data sheet for the cable, it will have the size of the cable, usually the diameter of the cable, or the radius of the cable, or its weight, which we can work out. It's AWD or SWG size, which is all equated to various sizes. If it's a square end of the cable, if the cable is square, then you just work out the area for a square and so on. So the area is pretty straightforward. So area, length, and resistivity. And what I'll do now is I will flash up a table of various resistivities. That's right here. There you go. Quick look at that. And for our wire, we're going to be using copper. It's, you know, the generic one. So copper is about 1.67 times 10 to the minus 8 ohms per meter. That's our resistivity. Okay, that's our constant value for copper. That value in theory is perfectly fine to use. It's based on the atomic element for copper. It's not going to change too much, but it will change depending on if there's any impurities in your wire, because I very much doubt that it's going to be a pure copper wire that you'll be using. And it's also going to vary with temperature. But for a ballpark figure, you know, this value is perfectly fine. It's not really going to deviate that much unless you do something extremely drastic to the material, okay, or the manufacturing process has gone completely doolally, or it's a right cheap crap piece of material that you're using. Okay, so it's cheapo stuff. But generally that figure is quite straightforward. So let's plug in all these numbers. So let's say the length of our cable is say 1 meter, and the diameter of our conductor is going to be say 1 millimeter. So the width, that's going to be our diameter, is equal to 1 millimeter. So our radius is actually equal to 0.5 millimeters. So plug all these into the equation, and yeah, we can work it all out. Just remember to set your units. So what would this come out to be? Let's go through this and work it out. Alright, so let's scrub this off the screen. Get rid of all of this. Okay, and R is equal to PL over A, which equals, let's start whacking in the numbers. So then, this will be 1.6 times 10 to the minus 8 multiplied by 1, because it's 1 meter. So just remember that P, this is in meters, length is in meters, and area will also have to be in meters. Make sure that you do convert everything to meters. This is a standard unit. It's no good doing millimeters, centimeters and meters, otherwise this is all going to work out completely useless. So 1 meter of cable, and so 1 millimeter in diameter for the area, area is equal to pi r squared, so it'll be pi radius of 1 millimeter diameter is 0.5 times 10 to the minus 3, because it's we're converting this millimeters into meters squared, so this works out to be, what does this work out to be? It's going to be a crap small number. 1.5 minus 3. Yeah, 2.4 to the minus, that's about 2.46, yeah, 46 times 10 to the minus 6. So our resistance for 1 meter will work out to be, plug in the numbers. Right, well, that cancels out, so it's just 1.6 minus 8 over 2.6. That comes out to be about 0.24. I'm missing a point. 0.024 ohms. Let's write that a little bit better on the screen. Just there. So R is equal to 0.024 ohms. There we go. That is our resistance of 1 meter. So 1 meter of wire is a length. The diameter was 1 millimeter diameter. The resistance worked out to be 0.024 ohms. Done. That's how you work out the resistance of a piece of wire. Its length, its area, which are the physical dimensions, and its resistivity you use. So moving on, how much current flows? Well, this is all down to Ohm's Law. So something completely new. Come on, are we gonna clear that off? Thank you. We've cleared it off and we're back in a row. So Ohm's Law. O-H-M. Ohm's Law. And just to iterate it, it is a law. And it's the one law that you need to remember. So what is Ohm's Law? Well, Ohm's Law is basically, it's the relationship between voltage, current and resistance. It's how all three of these are related together. And Mr. Ohm, one of the great-grandfathers of electronic engineering, okay, he found out and he stated that the voltage is equal to the current multiplied by the resistance. And you could change this equation about, so you get, you can either work it out for the resistance, which is voltage over the current, or if you wanted to work out current, it would be the voltage over the resistance. And he came up with this, that they were all related. So okay, yeah, they're all interchangeable. So if you know any of the two values, your resistance and your voltage, you can work out the current. If you know the current and the resistance, you know how much voltage you need, or how much voltage drop there's going to be, and so on. And this is basically Ohm's Law. It's a really, really simple little equation. It's very simple, or it's a very fundamental one, and you use Ohm's Law for absolutely everything in electronics. Everything is based on Ohm's Law, because we're manipulating voltages and currents, and it's all based on resistance. And yeah, and you can't have the one without the other. Let's apply that to our circuit. Here's our circuit then. We've got our voltage source of 1 volt. 1 volt, that's our wire. current is question mark, we don't know what the current is, and our resistance is 1 ohm. Okay, it's 1 ohm resistance. Well, what's our current? Current is equal to V over I, V over I, bloody hell, one more, there, V over R, I had brain fart just then. So what is it, plugging the numbers, it's 1 volt over 1 ohm, your current is 1 amp, done, simple, current is 1 amp. And let's knock it on the head. We're gonna have, let's do a different one. Let's say let's put this into a bit like real worldy sort of thing one. What can we do? Let's say we've got a 9 volt battery, a 9 volt PP3 battery connected to our circuit. We need let's say 3 amps flowing in our circuit. Okay, how much resistance should the circuit have to, for us to get 3 amps? Well, it was going to be, resistance is what we want to find out. We definitely want 3 amps to flow in circuit. We've definitely got 9 volts, so it'll be 9 volts divided by 3. It's really simple, which is, you need a resistance value, a resistor of 3 ohms. Now then, saying all this, okay, you can do the same thing for V as well. If you might as well top it off and just do V. You want, say, I don't know, 2 amps flowing in the circuit. You have a resistor of let's say 100 ohms. How much voltage do you need to apply? Oh, it's V equals I R, so 2 times 100 equals a voltage of 200 volts. Yeah, easy. What more do you need to say? Right, well, moving on from that, I don't know if you noticed, but your resistance of the wire, which we first calculated, was a very low value. Now, no matter what voltage that we apply to this, whether it's say 1 volt, which is a very low voltage, your current is going to be extremely high. So using wire as a resistor is not really that much useful. You would need absolutely tons and tons of wire in order to get to the current that you actually want. I mean, in this case 0.024, and we've got a voltage of 1 volt, so 1 divided by 0.024. Current is going to be 41 amps. That's a serious amount of current that's going to be flowing in a circuit. That's going to be almost all your source zapped instantaneously. If it's a battery, you'll probably explode the battery, or it'll be extremely hot, because you'll be drawing maximum current. You probably won't be able to get 41 amps from a battery anyway, unless it's something like a couple of car batteries. Definitely not at 1 volt, because a car battery will be 12 volts, so you might as well add on an extra 0 to the end, 110 amps if it's a car battery, 410. Enough to fry anyone. And yeah, this is why you can use car batteries for for melting metal. That's a serious amount of current, and it will probably melt the wire anyway if you try to do it. Anyways, yeah, so something like that is ridiculously small. How do we get around this? Because you can't use wire to create larger, well, you can use wire to create larger resistances, because what you can do is you can shrink the diameter of the wire down. By shrinking your wire down, you can increase the resistance, and you can also, so if area goes up, then resistance goes up. If length increases, then resistance increases. So, I'll say area goes up, increases resistance. What am I on? Area goes up. If the area goes down, you make the wire thinner, you increase resistance. As length goes up, you increase resistance. You can make the wire thinner to thin down a wire to increase the resistance, and you get less amps flowing and all that stuff. But you still need absolutely tons and tons of wire for that. You know, you need hundreds of meters of cable, okay, and hundreds of meters of cable just to say get to, I don't know, well, 100 times 0.24. You know, you can get up into a couple of ohms, but that's about it. A couple of ohms, there's still going to be a lot of current. Okay, so 100 times more length of wire means 100 times less. See? But that's still a lot of current flowing in your circuit, and it's a huge amount of wire, and it becomes unusable. So what do? We use the resistor, and that's what we're going to be going over next. So I'm not really going to go any further with this because I've been jabbering on for too long, and yeah, we'll cover resistors in the next one. I'll show you what resistors are, the first electronic component which you'll probably be using, different types, how they're constructed, and how you can get a lot of resistance packed into a very, very small space. And yeah, we'll start to do some, you know, a little bibbly and bobbling of resistors next. So see you next time.